you actually figured out what number? Huh? You said divided first. That's not right.
Okay, so remember what our goal was here, right? So our goal here, we're trying to come up with a rule for differentiating power functions, things of this form, x to the n, right? Okay, so we applied our rule for derivatives, the limit of the difference quotient, and the problem came here, right? When we had to expand, when we had f of x plus h, well, that's, how are we going to do that? That's x plus h to the n. We have to expand out x plus h to the n. And so we were trying to find a pattern for doing that, right? We know we're using Pascal's triangle, and we were making some progress. We said if we went down to the nth row of Pascal's triangle, we always know that the first coefficient is going to be 1. It looked like the second coefficient corresponds to n, and you guys had just figured out a trick here. You had just figured out that the third coefficient, right, so all the numbers in that third descending diagonal, all of those were the product of n times n minus 1, right, the row that we're on, times the row number for the previous row, divided by 2. Okay, good. So then we got, for the green one, we got n times n minus 1 all over 2. That's going to be the coefficient of the third term. What about the blue one? Anybody's, just for fun, I don't want to waste a lot of time on this because it's probably not necessary, but do you see how to come up with the fourth coefficient? And I'll give you a hint. It involves, so for the blue one, here's my hint. How am I going to get 20 out of 6? Multiply them all together and divide by what? Product of n times n minus 1 times n minus 2 times what? Or divided by what? 6, right? 6 times 5 times 4 is 120, divided by 6 is 20. 5 times 4 times 3 is 60, divided by 6 is 10. 4 times 3 times 2 is 24, divided by 6 is 4. So there is a pattern there too. What would be the powers of x and h in that next term, in the fourth term? X to the n minus 3, because that's 1 less than n minus 2, times h to the third. And we could keep going. The next one would be, what's that going to be? I think it's going to be, we're going to take the product of n times n minus 1 times n minus 2 times n minus 3 divided by 20. And we're just going to do that. And you could keep on going on and on and on. You're always going to find a recursive way to produce the next coefficient. But we don't need to keep doing that. We're just going to kind of ignore all the intermediate terms. Let's focus on the last two. What would the second to last term, the coefficient, be? And keep in mind, Pascal's triangle is symmetrical down the middle, right? So whatever we got, I mean, you already know what it's going to be. It's going to be that, right? Has to be, whether you walk from starting at the first term and walk to the right, or the last term and walk to the left, you're going to encounter the same coefficients. And when you get to the middle, that's where it reverses, right? You get what I mean look at these numbers. 1, 2, 1, symmetrical about the middle. 1, 3, 3, 1, symmetrical about the middle, right? See what I'm saying? So what's the coefficient going to be for the second to the last term? N, right? It's going to be n. It's going to be the row number, okay? So we get n times what power of x? That's the second to the last term. Well, what's going to be the power of x in the last term? It's going to be 0, isn't it? Like, look up here at this one. Right, I get down to the second to the last term, and the x's are almost gone. It's x to the 1. In the last term, the x's are completely gone. It's x to the 0, right? So I'm going to get n x times h to what power? N minus 1. And then the very last term would just be 1 x to the 0 h to the n, right? Everybody see that? Okay, so that's useful. We don't need to account for all these intermediate terms. We're going to find a trick. Did I have this? I did, right there. Okay. So let's look through, let's look through this process then. So here's where we left off, right? We expanded this out. X plus h to the n was all this stuff, right? All this stuff right here. That's x plus h to the n, right? F of x plus h. This minus f of x. So remember, all that stuff is really just f of x plus h. All that stuff. Okay, minus f of x. Okay, well, what can we do there, first of all? Can we make that simpler? Does anything cancel horizontally? Anything add to 0? Right?
X to the n.
X to the n. Yeah, look at that. The x to the n's are going to cancel. And we knew they had to because that's always how this works, right? The naked terms, the ones that don't have h's in them, always cancel. So I'm able to factor an h out of every other term, right? So we do that. We cancel those guys out. Every term has an h. What happens if I undistribute an h? What's left behind from the first term? Well, just that, right? N times x to the n minus 1. What's left from the second term? I've got an h to the 1. From the third term, I'm going to have an h squared left over. In fact, I'm going to be able to factor an h out of every term, aren't I? And the very last term would be left with h to the n minus 1. Agreed? See that? Now what? So I can cancel those, right? I remove the indeterminacy. And now I can take my limit as h goes to 0, and look what happens. Every term that has a factor of h in it goes to 0. What's the only one that doesn't go away? That guy, first term, right? So everything else went away. So we did it. We came up with we came up with an answer. Came up with a function corresponding to the derivative. And that's, what is it? So we know that f prime of x, if this is f of x, then f prime of x is equal to n times x to the n minus 1. Okay? And we could extend this. I didn't want to, the first time we did this, I didn't want to include a constant because it just kind of muddies things up. But if I were to multiply my original function by c, doesn't that just tack a c onto every single term? Right? When I evaluated this, I mean, c is being multiplied by, like, c times x plus h to the n just means I'm going to expand that whole thing I did and then distribute the c to each term. Big deal. The math still goes the same, right? I still end up, I'm able to cancel, we factor a c out of everything. I'm still able to subtract x to the n away to 0. I'm still able to factor an h out front with the c. I can cancel the h's, removing the indeterminacy. Let all the other terms, as h goes to 0, all the other terms go to 0. And I'm just left with that. Same answer with the c out front. Right? The math really doesn't change. I went through that pretty fast. I'll put these notes up. You probably want to take a look at this. Start getting used to seeing that kind of stuff, you know, where there's lots going on and just being able to follow the process of going from step to step. That's a big part of what you do in college. Math is being able to read a textbook, a math textbook, and be able to follow math as you read through it is just a skill that you just have to develop by doing it. It looks really intimidating the first time you look at it. Does that look intimidating? A little bit? Okay, but it won't. Once you start thinking about, okay, I'm just trying to see how this thing evolves from step to step. What are the individual algebra steps we're doing? It's no big deal. I mean, after a while, it just gets easier and easier to do. Before you know it, it's no effort at all. Okay, so let's practice this. We've got this rule. It's a really simple rule. Look at this. Here's another way of writing it. The derivative with respect to x of c times x to the n is that. That's my derivative function. Okay? You see how that's a little bit different way of expressing it than this? Well, I guess that is how I expressed it. Instead of saying, here's one way of saying it. If this is f of x, then f prime of x is equal to cn x to the n minus 1 power. So we write the derivative function out. We write f prime of x to represent the derivative function. Okay? The other way we can write that, the other notation would just be this. When I see derivative with respect to x of something, that just means I'm going to take the derivative of whatever's behind my hand, and what do I get? It acts like an operator, right? And that's what the derivative is. Think about that. That's easy. All we're doing, if I have a power function, if I want to come up with a derivative of some constant times x to the n, what did I do? Whatever the exponent was, I just pulled that out front as a coefficient, and I subtracted 1 from the exponent. Easy. So if this is f of x, if f of x is x to the 12th, what's f prime? 12x to the 11th. That's it. Easy. Super easy. You drop the exponent down as a coefficient, subtract 1 from the exponent, and you got it. Okay? How about this one? F of x equals 3x to the 4th. What's f prime of x? 12x to the 3rd. That's it. Right? You drop the 4 out front, and it's a coefficient, so 3 times 4 is 12x cubed. How simple. Do you prefer that to having to go through and doing the limit every time? I sure do. Yeah. Okay, now the next trick is, so we've got these, here's the one, I mean, everybody see that really this version in the red box absorbs that one. We don't even need that one anymore. That's just the case where the constant is equal to 1. We want to pick the most general one. So now the next issue is, how can we apply this to functions where it's not just immediately obvious that it's a power rule derivative? Like, what about this one right here? How would we do that one? Because it looks like we're going to require some new derivative form for some kind of a quotient or something. Right? Is there a way? So this is oftentimes the goal in calculus. The rules are simple. The derivative rules we apply are really not very hard. The tricky part a lot of times is writing the expression in a way so you can see that it applies. Sometimes I call it pre-writing. You're going to write this function in a way so we can see that this rule applies. Because it doesn't look like it does right there. How could I do that? Could I write y in such a way that it looks like a constant times x to a power? This one. Okay, but I need it as a power. X to the negative 1, right? X on the bottom is the same as an x to the negative 1 on the top, right? Aha. So if we write that as 2x to the negative 1, well then, what's y prime equal to? What's the derivative? That's just another way of saying derivative, right? We'll follow the rules. What is it? Negative 2 x to the... What's my rule say I do? I subtract 1. Negative 2. Negative 1 minus 1 is negative 2. There's my answer. If I want to write that without negative exponents, I would just write it like that. Okay? See? All right. How about one like f of t? What part looks confusing about that?
X squared over t squared over 5.
Say it again. The t squared over 5 part?
Yeah.
Okay, so yeah, when you see stuff like this, the variable is in the numerator. The 4/5 is just a coefficient, right? A constant on the bottom is the same thing as multiplying by a fraction, right? So here's how you want to think about this one. You want to think about this one as being 4/5 times t squared, and it's easy, right? Now, the 4/5, you just leave that out front. What did we do in our pattern up here, right? Our derivative formula. The c, just whatever the constant is, just stays out front and gets multiplied by n, right? So the 4/5, it's just out front. It just stays there. All you have to do is take the derivative of t squared and multiply the result by 4/5. What's the derivative of t squared? T's our variable instead of x, but it's otherwise the same. 2t to the 1, so 2t, right? So this is just equal to f prime of t then, right here I guess, would just equal 4/5 times 2 t to the 1, which is just 8/5 t. So how do you think about that? You just leave the 5 on the bottom, you multiply the 2 times the numerator, and you get the coefficient 8/5, right? Give me thumbs. How are we doing on this? Okay. What about the derivative of, what if f of x is 6x? The answer is just 6. How come? Well, because look, I'm going to take the 1 out front. Out front, I just get 6 times 1, which is 6. X to the 1 minus 0 is what? What's anything to the 0? 1. Okay? Right? Make sense? Okay? How about that one? That does not look like the power rule should apply, but it does. X to the 1/2. Yeah, if you have a radical, you just turn it into a fractional exponent and you use the power rule. Okay. So we would want to rewrite this as 2x to the 1/2. So what's y prime going to equal then? Just follow the rule. What do I do to the exponent? Well, I drop it out front. 2 times 1/2 gives me 1. X to the 1/2 minus 1 is negative 1/2, right? So that's my answer. The derivative equals x to the negative 1/2. Okay, well, what is that? A negative exponent does what? Puts it on the bottom. 1 over x to the 1/2, which is 1 over the square root of x if I want to write it as a radical. Okay, make sense? That's no big deal. That's no big deal. So you gotta pre-write it, right? You gotta write this in a way where it looks like a constant times the power. Okay, yeah. So focus on this part.
1/2 x to the negative 3rd.
Yeah, there you go, right? would you agree the cube root of x squared, everybody see that? The cube root of x squared is the same thing as x squared to the 1/3 power, right? Which is the same thing as x to the 2/3, right? That's on the bottom, so it becomes negative, and we just get 1/2 x to the negative 2/3. Okay? So what's that going to equal if I take that derivative?
Okay.
How did you go from the x to the 2/3 to the parentheses?
Well, okay, so this is everything that we're taking the derivative of, right? That stuff is just right there. Okay.
Why is it negative 2/3?
Because it's on the bottom, so it's negative, and a cube root of x squared is a 2/3 power. So what's my coefficient going to be? Negative 1/3. How come? Because I've got 1/2.
Because look, it's right there.
1/2 times negative 2/3 out front times x to the negative 2/3 minus 1, which is what? Negative 5/3, yeah. So we get negative 1/3 x to the negative 5/3, right? Whoops. Sorry. Okay, make sense? How could I ask a question?
Can we do a board work?
Sure.
Do we need to
Yeah.
do we need to rewrite that?
We do. So let's practice that. But first, we'll go to the board in a second. First, let's make sure we can wade through this. Right? So I've got my exponent, right? Okay. Hey, there we go. So I've got c times x to the n. That's my n. I multiply the n times the c. So 1/2 times negative 2/3. That's going to give me my coefficient. That's negative 1/3. I'm going to subtract 1 from my n. So n minus 1 would just be negative 2/3 minus 3/3 is negative 5/3. Okay, I'm just following the rules. That's the derivative, right. And if I wanted to rewrite that, I could have a 1 on the top, 3 on the bottom, and then this part. What about that part? X to the negative 5/3 is 1 over x to the 5/3. And so that just becomes negative 1 over 3 times the cube root of x to the 5th if I wanted to write it as a radical.
Will we have to in or everyone look at my friend when we have to
I don't want your friend exponent and put it into a fraction, or can we leave it?
What do you mean?
Like in our homework, I know.
So which part are you, do we,
the part that's in the orchard, right?
Yeah.
that part?
To leave it like that, or do we have to change it for the?
It's probably going to say write your answer with positive exponents. So you would just have to put it on the bottom.
Stop it right now.
Yeah. Okay.
Include the radical and the cube root, or could we just do 1 over 3x?
I probably could just leave it like that, I bet. Yeah. It's important to know that connection to the radical, though, because that will be something that we're going to rely on quite a bit. It's important to be able to write it as a radical. Okay, so why don't you try, I'm going to give you one. Go try this on the board.
Okay, and it's y equals. Negative 2 over 5. Expand the fraction marks. 5 root. How would I say that? 5 root?
5th root.
Fifth root. Oh.
Go.
So what? So it's 2. This is what I'm
Okay, how about this one? Yeah.
Not that long of a time.
Oh, sure we do. This one won't take long. So interpret that. What's that mean? So let's just focus on this part first. Let's look at the function.
So R would be X.
Okay, so R is, the input variable is R, right? You have this function A as a function of R. So what you're calculating here, dA dr, that's just another way of saying A prime of R, right? Those are interchangeable, just different notations. They mean the same thing. So this is really easy. What's this equal to? This is much easier than the last two you guys just did. 2 pi r to the 1, right? Pi is the coefficient to begin with. That's like, there's my value of n, so I'm going to bring the exponent out front as a coefficient. So I get 2 pi r to the 2 minus 1. I get 2 pi r. Okay? Is there a, no. Okay, how about this one? Okay, now what looks complicated about this? Okay, there's a bunch of different terms, right? Okay, does that really make it more complicated though? How do you think we deal with a derivative of 3 separate terms like that? Yeah, we just differentiate term by term. If we were doing a limit, couldn't we split the limit apart? So we can split the derivative apart, right? All we'd have to do here is just maybe distribute the -2, so we get 3 separate terms, and then you just knock them off one at a time, right? You just look at them each individually. So if we distribute this -2, that's just going to give us -6x to what power for my first term? -1/3 plus 14x to the 4th minus 10. Okay? Well, let's differentiate those term by term. So what's the first one going to give me? So I get -6 times -1/3 is, well, +2, right? +2, x to what power? -1/3 minus 1 would be -4/3, right? Plus, how about this one?
56x to the 3rd.
Good. How about that one? The power rule does apply, but you don't really have to. So that would be the same thing as -10x to the 0. So if -10x to the 0, if I took the 0 out front, what am I getting? 0. So the answer is 0. Okay, but you don't even have to make it that complicated. The derivative of a constant, think about this in terms of, it's just a general rule we have. We're going to add this to our list of derivative rules that we memorize. This is a really simple one. The derivative with respect to x of a constant is always 0. Think about why that is. If I look at a graph of the function y equals c, there's the graph of y equals c. It's a horizontal line. What's the derivative of that function everywhere? Derivative equals slope. No matter where you go, the slope of that function is 0, right? So that's another way of convincing yourself that the derivative of a constant is always 0. You can use the power rule, but it's overkill. Okay? All right. How about this one? What's the derivative of ax squared? 2ax. Yeah. What's the derivative of bx? What is it? Just b. Yeah. Just b. Right? Because the derivative, another one we could add to our list, the derivative with respect to x of x is what always? 1. Okay? And this is kind of tricky. I mean, don't think this, you can always just say, okay, another way to rewrite that would be the derivative with respect to x of x. Well, what do you think dx over dx simplifies to? Simplifies to 1. Okay. Don't, that's just kind of a little consistency in the notation. But the way to think about it is using the power rule. That's x to the 1. Bring the 1 out. I get 1 times x to the 0. X to the 0 is 1. So it's 1. Okay? So that's what we get from that one. Okay, how about this one? Last one. Find the equation or equations of any horizontal tangents to the curve. That seems like a tough problem, right? We got to figure out, we don't even know what this curve looks like, but we've got to find the equations of all the horizontal tangents. How could we do that? Seems like we're going to need, to find a line, we need a point and a slope, right? Okay, so we need the derivative to find the slope. So there, we're going to need to calculate a derivative. So what's the derivative of that polynomial? We just differentiate term by term. First term gives me 6x, good. Minus 12, and then the last term, derivative of 4, is 0. Okay? All right, so I want to find all the places where that has a horizontal tangent. Okay, well, what horizontal tangent, that's a loaded term there. Horizontal tangent tells me something really important. Horizontal line has a slope of what? Okay, so we want all the places where the function has a slope of 0. How could I ask the math gods for those locations? The math gods are not amenable to begging, no. What would I do? I want to know, where does the function have a horizontal tangent? In other words, where is the slope of the tangent line equal to 0? Set what equal to 0? The derivative function, right? How come? Think about that now. Just focus on that concept, everybody. You got to walk out of here today with that light bulb turning on. If I know that the derivative function is 6x minus 12, think about the job of the derivative function. The derivative function is always going to give me the slope of the function for any input value of x I choose. I want to be able to choose the value of x where the derivative is equal to 0. So all we have to do is set the derivative equal to 0 and solve for x to find that place, right? When I set the derivative function equal to 0, we're asking the math gods, where is the derivative equal to 0? And they answer through an equation that we can solve. So what's the answer? What's x equal to? Yeah, I solve that equation, I get x equals 2. Beautiful. So we know the location, that's the x value where the derivative has a horizontal tangent, right? I need to know the y value too, though, don't I? So how would I find the coordinates? Yeah, plug it in there. And we're going to get f of 2 equals what? 12 minus 24, so negative 12 plus 4, negative 8, right? So what's the point of tangency? 2, negative 8. That's the point of tangency. What's the slope? We already know what the slope is. 0, yeah. So then if we just use the point slope formula, y minus negative 8 equals m, which is 0 times the quantity, who cares really, x minus 2, but that's just 0, right? I just get y plus 8 equals 0, so what's the equation of the line? There it is, right? Yes, sir?
I know we should know this, but can you go back over how to get the derivative of the black equation?
Yeah, so we're using the power rule. We've got each of these are, each term we can differentiate with the power rule, generalized power rule. The derivative of 3x squared is 2 times 3, which is 6, x to the 2 minus 1. Derivative of negative 12x, there's a 1 there, right, is 1 times negative 12, x to the 1 minus 1, x to the 0. So that's 1. And the derivative of a constant is always 0. Yeah. Okay? Make sense? Okay? All right, you got a work day tomorrow. You got some work to do, so that's a good thing.